Okay, good evening. We'll be waiting for 1 2 minutes. Maybe someone else will join, and then we can start today's session. Is that fine with you? Is that fine, Newton? Am Am I audible? Okay, let us wait for some time, and then we can start. Okay, so we can start today's session. So my name is Adnan Farooq Khan, and I am a PhD scholar from IIT Delhi. And this will be like a week 8 of our problem solving session, and this is the last problem session that we'll be taking for this course, because like the course has been completed as of now. So today is our last like session of problem solving session, and the other problem solving session that had to happen in this course had already taken place. That was on Monday and Tuesday, like from 6. So this will be the last problem solving session for this course, and if you be having any question, and you can ask. So yeah, I'm Adnan Farooq Khan, PhD scholar from IIT Delhi. Once again, I welcome you to this problem solving session on Monday. So I'll every other Monday, this is a problem solving session for the Advanced Power Electronics and Control course, which is being taught by Professor Avik Bhattacharya. So like every other problem solving session, in this problem solving session as well, I'll be talking about like what has been taught in the previous week, like about power quality problems, what was discussed briefly. I'll be telling you. Then something about linear and nonlinear controls that I'll be briefly touching this course, and some applications that had been discussed, and we'll be concluding with some numericals that we'll be taking at the end of in this like problem solving session, that will help you in solving like today's problem. Numericals are like based on overall what has been taught in this course, rather than deeper towards these particular topics. So about the power quality, like coming towards the power quality first before going to the linear controls. So I'll briefly tell you about the power quality. Why is it of utmost importance? What we were seeing, like have been seeing throughout this course, like because of this power electronics converters, like if you are having a diode bridge, if you let us say take a simple diode bridge rectifier, you saw that uh, what we had a distorted sort of a source current, and what we discussed is like it could affect the, like when our source current is distorted and at the point of common coupling, like many of the devices are attached to it, and be it some other PWM converters and some other converters that are connected to the grid. And what we saw is like we had with different PWM techniques, we had like harmonics and like some power factor in our grid current. And you could say that because like if our grid is not at unity power factor, like if it has some uh, um, power factor of a we have a converter, and the current that's come to this like of this the converter, the source current will be having, if it draws like both active and reactive power. We only know that active power is only the useful power, and this reactive power is not the actual power. and because of this reactive power, like we have like some additional current will be drawn from the grid, which can in turn like in turn increase our losses, and which can decrease our efficiency. Besides this, what we saw is like with respect to power quality, like because of this power electronic converters, like we had like a harmonics were also present, and due to this harmonics, what we wanted to do is we wanted to eliminate this harmonics. And we don't only have this power converters attached to our grid, and at the point of common coupling we'll be having some sensitive like devices, like measuring devices and protection devices that are connected to that as well, and those harmonics can affect those devices. And besides this, we are having like we can have an EMI issues as well. So in order to mitigate, like we wanted to reduce this harmonics and active reactive power. In this, what we use what has been taught in this course. You can go like most of it was theoretical, that's why like I am discussing it overly. Like we can use different filters, we can use like different filters, types of filters that has been discussed in the course to like eliminate these harmonics. And we can have this like active compensation as passive compensation as well for our reactive power in order to compensate for that. So yeah, like this power quality is an important issue, so we always want to have improved power quality. If we want to improve our power quality, like there are certain techniques like that has been taught in the course. You can go through the course lectures, like most of it was the theoretical. You can like see the transcript as well as the presentation, see the different techniques of like power quality mitigation and improvement. And now coming to the other part is like the linear control. So the control aspect of the controller of the converters is very important in a sense. Like ultimately, like we want we want to design the controller for our converter, so that whatever like if we give some command to this controller, like we want, let us take an example of a buck converter. So we want a certain voltage at the output, be it any with any change with load or something else. So we want our converter to operate about that particular operating point, whatever we is our need. We don't want our converter to deviate from that point. So what we missed, someone has recently joined. Can you please like turn off your mic? Can you please turn off your mic? My experiments is the name, like. So we want to design the converter. For that, like we want to design the controller for the converter. Like we want to operate our converter at a particular operating point, and we don't want our converter to deviate from that to have a robust operation. So what we will be discussing here is the linear control, like what had been discussed in during the course. Like you were taught about like the different approaches, like of a state space approach and a transfer model approach that has been taught in detail. Like I'll briefly like go through what are the different steps that we do in order to realize a system first, and then we can design a controller for uh, certain like what we want to control. We can and what the variable we want to control, and with what, like if we want to like for example in a buck or a boost converter, if we want to control the output voltage with respect to change in the duty, so we'll be so how we'll be getting to this control the output transfer function, how will we like what are the steps that we take place that we take part in to come up with that transfer function, and when we get that transfer function, that would define our our converter, and then we can design our controllers with that for that particular system that will constitute our system. So I'll be going through that. These aspects are these topics are in very detail, first coming deriving these equation transfer model. Like, this is a very vast topic, and if you want to study it in detail, you can consult this book by Robert Erickson, Fundamentals of Power Electronics by Robert Erickson, and you can see how in detail you can see how this modeling and all is done. And besides this, there are certain aspects as well, then how we'll be uh, doing the control of how we'll be developing our controllers for a certain converter. If we have the transfer function, there are certain techniques that we go, like Bode plots and all. And with the Bode plots, what we'd see if our is system is controllable, with that we see different things like phase margin, gain margin. If we're this is an advanced course, in some course of control you would have seen how we design this controller from the Bode plots and different techniques like that. So yeah, for this linear converters, if we want to design the controller for, or get the controller for this a certain converter here, I'll be discussing an example of a boost converter. Just a minute, sir. So here I'll be discussing about the boost converter. So how we will be forming the transfer function of that, and how we will be designing the controller. The first most step is what we have to do is we have to demodel the converter. So we have to write the equations, converter equations, in different subintervals. Subintervals means our converter will be having a D interval while one switch is on. Then what we saw is 1 minus D interval, where some other switch is on. So first and foremost thing what we'll be doing is we will be writing the equation for these intervals, the average equations for this, like we had seen for the Bach and boost converter during the DC-DC converters. So after that, what we'll be doing is we'll be doing the averaging of these equations, and what we do is we will use an approximation here. Will you can see, if you could see in the current in the Bach or a boost converter, that was having some ripple. So what we will do is what we will be using, we will use an approximation like that. We'll have a small or linear ripple approximation. That what we'll assume is that our ripple is very small. So what we can assume is our converter is our any current or voltage is closer to its average value. That is the approximation that we consider here. Afterwards, what we do is we do the perturbation, we add some disturbances to certain parameters and see how our converter or this transfer function, which ultimately defines the converter, will respond to it. And we linearize those equations about a certain point or quiescent point or some optimized operating point. We do this linearization, perturbation, and then we linearize these equations. So when we do that, and ultimately we'll be getting the transfer function of that I'll be showing how we will do that for the boost converter. And after that, what we do, when we get this transfer function of a certain parameter with respect some other parameter which we change, and we want to see how one variable changes with the change in other variable, then what we do is we that transfer function defines our converter operation, and we want to design the controller for that, like with respect when we change certain thing, and when this changes, so we'll be designing the controller for that. So we'll be seeing, and I told you, like we use like different techniques for designing the controller, like a Bode plot technique is one such technique. If you have a transfer function, we design the Bode plot, we draw the Bode plot of that, and we see, then we have a like a controller transfer function, and we design the overall transfer function of the system. Then we draw the Bode plot and see if our whole system is stable or not, based on like a different parameters like phase margin, gain margin, and if you could like see any control book on that, like control book like something like Norman Nice or some other book, or if you have taken some course on the control, like about this, so there you will see it in detail, or you can see one of the books is like one by Norman Nice. You can consult that book for this Bode plots and all. So let us come to the steps, how we do this control for the example of a boost converter. Here you can see towards the left is the boost converter, like we have a DC source, then we have an inductor, and then we have a switching network, like we have two switches. Then towards the load side we have a capacitor, and the resistor as a load, like this capacitor is to as a filter. So if you can see in the D interval what happens, like this switch is we have our like circuit in the D interval is this, like we have this switch is turned on and this switch is turned off. So what we do is like energy is getting stored in the inductor, and at that time like the energy to the load is fed by this capacitor, and this is our for this D interval. So in the 1 minus D interval or D prime interval is like 1 minus D, like if we have a switching period of Ts and we switch it on for certain dts time, like d dash is will be 1 minus dts time. So when we close this, so in d dash interval what we do is this switch is turned off and this switch is turned on, and we'll be having this, and here you can see then the voltage across the inductor will be V in minus V out, and you can see this is the circuit that will be formed in the D dash interval. So the first step what we will be doing is, like I told, first we will be writing the equations for like different intervals. Like we are here, we have two intervals like D interval and D dash interval. What we will be doing is we will be seeing what will be the voltage like across these like current through the capacitor, and the average voltage across this inductor and the capacitor. Like we saw in the previous lectures, we'll be first writing the equation for this D interval and D dash interval. So coming to the D interval, like I told you, in the D interval the switch will be on. You can see that VL will be equal to V in this D interval, and what you can see, we will leave this D dash interval for the time being. We'll be talking about this VL interval only for the moment. So just a minute. So like we'll be having VL, like this will be equal to V in this D interval. Also, if you can see, we know that the current through the inductor cannot rise immediately. Like you can, will be having this IL will be equal to, that will be equal to since this will be having a like a linear rise from some value to the peak value. And this other approximation what we had assumed, like our ripple will be very minimum. Here we have shown some ripple, like it is only to show there is some ripple, but what the assumption we are taking during this driving the doing this linearization, we will assume that the ripple is very less, and we can assume that the current will be equal to the average value that is shown by this gray current. Also, we can write the equation for the current through the IC. You can see this IC will be equal to negative of the output current. So that will be equal to, output current will be equal to whatever the output voltage V out by R. So IC will be equal to minus of V out by R. So we got the equation for VL and IC, that is the current through the capacitor for this D interval. So this is the first step, like we got the equation for the D interval. Now we will be seeing about the D dash interval. So in the D dash interval, what we will be seeing similar things here. So we will be seeing the voltage across the inductor. Here voltage across the inductor will be V in minus V out. So if you can see, this is the loop here, or here, like this V out will be across this as well. And also we know that the output voltage is greater than the input voltage in case of a boost converter, so the overall voltage will be negative. So in this interval the voltage will be negative across this inductor. So what will happen, like the current, since the voltage impressed across this inductor is negative, that means the current will start to decrease, initially, in the D interval, since the voltage was positive across this inductor, current will gradually rise to some peak value until when this voltage goes negative. That means now the current will start to initially what the energy was stored in, now it is like giving out the energy, so the current will start to decrease to the previous value, that is across the this VL. Now what we'll be seeing, what will happen to the IC. So initially what we saw is like IC was equal to minus I out, that is equal to, like this is the IC, this will be equal to minus I out, this will be out by R. You can see, since this is a resistive network, that this will be a constant here, so it is like a constant current here. So in D dash interval, we can see IC, if you apply KCL here, IC will be equal to, we can see IL is coming from this into the node, and out of this node, like I out and IL is coming out. So you can see IC will be having this shape. IC will be equal to IL minus I out, that will be equal to IL minus V out by R. So it will have the shape of this IL, but with some DC component that will flow through the load, that will be subtracted from it. So it will be having this kind of a shape. So in this also in this D interval, since this is supplying this load, V out will decrease, and in this we are feeding this current into this is like a positive current. That means that capacitor is getting charged. In this interval, capacitor was getting discharged because it was feeding this load. So this is the IC and V out waveform for these two intervals. So this is the first step. What we got is the average equations in different intervals in this for this converter system. What is the next step that we will be doing is we will be averaging this for this VL and IC, will be doing the averaging of these equations like we do for every other case, like a buck or the boost converter. Here you can see we got the equations that we got are here in D, and 1 minus D. We'll be first writing the equations for the VL. The average of the VL will be equal to it will be equal to D into V in average. Well, why we are writing here the average? Because we are taking the assumption that the ripple is very small, and we can assume that this value, the value of these variables will be equal to the average value. Here the ripple is shown like in order to make you understand, but here the assumption is taken like the ripple is very small. So we can take like we will be like replacing these variables with the average values. So that will be equal VL will be equal D into V in average, like plus D dash in this D dash interval, like VL is equal to VI minus V out. So D dash will be equal to in plus D dash into VI minus V out. So when we have this, similarly we can write the equation for the capacitor. We have this IC. We have like this is the like charge balance equation, but we are doing the averaging of it. So you can see we have IC is equal to minus V out by R for the D interval. So for D will be getting the average of this minus V out by R. In the D dash interval we'll be having IL minus V out by R. So in the D dash interval, like we'll be doing IL average minus V out dash by R. Because like average here, I'll once again reiterate, because like we are doing the assumption that ripple is very small, and the value of this will be equal to the average value. So here we can replace, we know that D dash will be equal to 1 minus D. So if we replace D dash by 1 minus D and solve this again, we can get this equation. VI will be VL average will be equal to VI minus D dash into V out. And similarly, if we substitute like D dash equal to 1 minus D, so we can get like this equation for that as well. And that will be equal to VL, and we know that VL will be equal to L di by dt. So this is our one equation, and we know IC is equal to C dV by dt. So this is our other equation. So here we got the two equations after averaging over the complete switching cycle. That this is like the average we do for a one switching cycle. Here we have like D interval and D dash interval, like that would be equal to 0 into T 0 to TS, and this point will be equal to DTS, and this is 1 minus DTS. So after averaging these over a one switching cycle, these are the equations that we get. So once like we get these equations, what we do is we do this perturb. So here you can see there are a set of variables like we can have is like we can perturb like this D by some small amount like D hat, and see what is the change in the system. Similarly, what we can do is we can perturb this input and see what will happen. Also, let us say if there is a small perturbation in this inductor current or in the output, how would our like systems will do. So what we want to do is, what we'll be doing, we'll be replacing each with these like D we will be replacing by this D, this is the average value, and this is by small perturbation. Similar for all other variables like V in and all. So when we'll be doing this, and we'll be solving this, and you can go through, like I told you, like the derivation is a bit long. You can see this you can go through this book like Power Electronics by Robert Erickson. Like this is all mathematical. After like replacing by this, and you can see when we will be here, we will be getting these equations like dIL by dt will be equal to like you will be like seeing it will be like this equation here. What we have assumed is we have like neglected the DC components because they will get cancelled, as will see when we will solve these things. And also what we have done is we have, when we'll be like seeing, like here you can see there are only first order terms. So whatever the relation will be having a linear relation. Also, like we if there will be, when we'll be like replacing these with this, d with this, and all, we'll be getting some second order equations. Like we'll be having v naught cap or into like multiplied by d cap. You can see already we have assumed like this perturbation is very small, and if you multiply this perturbation with some small perturbation of some other small perturbation, the value of uh, the parameter will be very small. So here what we have assumed is like we have neglected that as well. So here we have only taken this first order linear terms only, and you will see like we'll be getting some DC terms, some first order linear terms, and second order DC terms. DC terms will be second order AC terms, that will be non-linear. So we have, because those non-linear terms will be very small, we will omit them, or we will not take them into the consideration, and the DC terms will get cancelled out as you will be doing this. You can see from the left hand side and right hand side they will get cancelled, because the average will be the same. So overall we'll be getting this equation which will be having a linear dependence. So you will be seeing like that means that now we have linearized this these equations about some operating point. And because we have like done the perturbation about some average, like that this is some average point, we have given some perturbation about that average point. Like if we now we will be seeing how our system will respond if we're doing some perturbation about that point. So after that, like you can write these state space equations for this. Like now you got these two equations, you can write these state space equations for that. And for that, how to write the state space equations, you can like go through the lectures and follow these steps. And there it has already been taught. Now how we'll be getting a transfer function. Let us say here is the transfer function. One of the transfer function that we want to get is v out cap by d hat. That means this is a control to the output transfer function. That means we want to see with the change in d, our we want to control our output with the change in d. So this will be our transfer function that will define our system. So if we want to control our output with respect to the change in d, so we'll be now designing in a similar fashion. Like we can have our transfer function with respect to I, v in, and so on. You can see different transfer functions, how they are formed when you go through the notes that has already been taught, or you can consult the book Power Electronics. Like if I go into that, that will be in much detail, that will be take a long time, and I will have to go into much detail. Here I want only give the overview. So now when we get to this equation, now what we want to do is we want to control this. So this will be our, now this v out by d, this will constitute our vd. So this is now will be our system, and input to this is this d. So and at the output, like we'll be getting some v out. So gvd will be equal to v out by d. So that is this transfer function, as you know. So now what we want to do is we want to do the closed loop reference. So we want to have a certain reference this, and we want to regulate our output to this reference. Let us say we have given, let us say 50 or 100 volt, and we want to regulate our output to that voltage. So what we'll be doing is like we'll be taking a feedback loop from this. I will be sensing the output, and then we'll be having this some sensor gain. This is nothing but some HS is like a transfer for function, like a sensor gain. And here we'll be doing some we'll be comparing it, like and an error will be generated here when and this error will be fed to the controller. So controller will then measure this error, and what it would try to do, it would try to minimize this error. So it will like generate some signal, and which will be fed to the PWM, which will then subsequently generate our duty pulse, like a duty pulse for the converter, which will then regulate our uh, voltage to the reference point. The whole point is now how we can generate, like what will be the controller, like that is the different aspect. Like there can be a like a simplest of the controller is this the PID controller. Then we can go some higher order controllers, and here I won't go into that detail, but this was like the brief thing that what needs to be done in order to like do the control of this converter. Like we first have to write the equations, come up with the transfer function that we want to control, uh, appropriate transfer function of the specific parameter that we want to control with respect to some other parameter. Then we will be like designing this controller that would try to like minimize this error between the reference and the sensed output. That will generate some signal that will be giving that will generate some reference that will be giving to this PWM, which will then generate our duty to the converter so that our output is regulated. That was like the overview of what we want to do about the control and all, and about the applications and some other things that will subsequently what had already been taught about the different applications of this electrons that will subsequently come in this for this that will come in the subsequent questions where we'll be discussing them. So that was about this what had been taught in the previous week. So yeah, now we'll be starting with this problem solving session, and before problem solving session, like, let us take a break of like 5 to 7 minutes, and we can start on 7:55 or 7:57. In the meanwhile, like you can see this question number 1 and can think what can be the answer of this question. So yeah, we'll be joining back at 7:55 or 7:57. So yeah, we can start. So coming to the first question, what is used for the critical loads when temporary power failure can cause a great deal of inconvenience? So here the critical loads, like, can anyone answer first? Like, there are different options that are given, like SMPS, switch mode power supplies, MPS, UPS, and RCCPs. So first, like, critical loads means like we wanted to have the continuous supply to our load, and the supply to the load shouldn't get interrupted at any point of time. That would cause great source of inconvenience, great deal of inconvenience, or can cause damage to our converter, and so on. So let us first see like how this, like, a linear power supply will looks like. Here what we have, one of the supply is like, we will be having a linear power supply. There what happens is, like, we'll be having an input of some sort, like an in single phase AC, and if we want to like operate, get different power levels from this, let us say we want to have different, like we have a 230-volt input and we want to have operate our chargers with it, like we want to have a lower voltage levels and lower or different voltage levels. From that, what we first needed to do is, like, firstly there is like a transformer here, that will be a low frequency transformer designed at a low frequency, and like this transformer size has an inverse relation to this frequency. Higher the frequency, the size of the transformer will reduce, and here we have to, like, design this transformer for, like, for 50 hertz. So it will be having like of this transformer will be of larger size compared to some transformer that will be of higher frequency. Then what we do, when this is stepped down this voltage, then we have this like a full diode bridge rectifier, and by this, like, we'll be able to generate like a DC output voltage here. And if like this DC, then we'll be having some series regulator or a low pass filter, like, so we don't have this high frequency components, and we'll be regulating it around a certain that is needed here. And here you can see, like, whenever, like, this works only whenever there is an input supply, and when this input supply gets cut off, then this cannot work this cannot work. uh, and another one is like a switch mode power supply. Similar to this, in the switch mode power supply, what we have is, like, if you want to have a DC voltage of different levels and so on, we'll be having, for what we first do is we do first AC to DC conversion, and then we can have a DC to isolated, like a isolated DC converter. Here you can see we have a flyback converter, and you can see like this transformer, or like you can see a coupled inductor, is designed for very high frequency. We can see, like, we have designed this this is like at very high frequency, so the size of it is very small compared to this. And you can see, like, the switch mode power supplies will have, like, lower losses compared to this linear power supply. But you can see here as well that this is like this network will work only whenever we have an input supply. When this input supply is not there, so we won't be having, like, we won't be having any, like, this DC voltage, and we won't be having any DC output. So in case, like, of like when we have when the input supply is not there, these two like won't be able to work. So another one is like an UPS, that is an uninterrupted power supply. Here what we have is like, you can see the configuration of it, like it is first like, and what we do is like an AC to DC conversion, but here instead of having a like a DC link, we will be having a battery here that will store this energy. So when this energy is here stored in term, and after this we have another stage, that is a DC to AC stage. As an inverter, we can have mm, the output from this stage, DC to AC stage. What will happen like when this AC is not, or input is not there at that moment? What will happen, like this DC will feed our loads, and we'll be doing an inversion operation here from DC to we'll be doing a DC to AC conversion. Like we'll be having we have a battery, and this from this we'll be having a converter that will be doing generating an AC at the output. From this, like we'll be like supplying to various loads, be it low or high. Also, we can have another like direct connection from AC to AC. Whenever like we have the supply is there, like we can bypass this stage, and at that time we can have a direct AC to AC. It can feed direct AC power. So in terms of when there is no input, at that time we'll be utilizing this battery and having this inversion operation that will be driving the loads. So here you can see, for the linear power supply or switch mode power supply, we need to have this input at uh, all the times to like drive our loads. And here you if our input is not there in UPS, like you can drive our loads as well, like from this battery, by having an inverter here doing an inversion operation. So here you can see for the question number 1, like C option is correct. Coming to this another question, like question number 2, we have in HVDC transmission lines, what we'll be having, both the stations operated as an inverter, both the stations operated as a converter. Like one of the acts as a converter and another acts as an inverter, and the last option is depends upon the type of the load. So this hasn't been, like HVDC hasn't been taught, like one of you has said the option C. So like this wasn't taught in the course, and I don't expect like you to answer this question, but if someone knows, that is quite good. So we'll be seeing what happens in this HVDC transmission. So we'll be seeing first like why we go for HVDC, and then why we want to do this DC transmission, and how this DC transmission is done. So firstly, the question that is why we like go for this high voltage power transmission. So firstly, like we'll be having, you can see like we have a generating stations, be it with the hydel power generation or thermal power generation, we'll be generating the AC at certain voltage. And the first thing that what we do is like we step up these voltages to higher voltage levels and then transmit them. So can anybody like tell me what is the reason that we step up this voltage to such levels? So if anyone can answer, like why would we go for high voltage levels in the transmission line? So I would so the idea here is like we want to transfer certain amount, like we are generating a certain amount of power and we want to transmit that amount of power. So we know that this power is like a product of this voltage and the current, and the power is constant to us. So if one of the parameter increases, the other parameter has to decrease so that the power is constant. So what happens when we will be increasing our voltage? So when the voltage is very high, that means the current will be very less, the current will decrease. So as we increase the voltage, the current will start to decrease. And the idea behind like having a decreased current and having a high voltage is like, you can see this transmission lines, they run over hundreds of kilometers. And you can see if we will be having, and these cables will be having some resistance. So if we'll be having very high current that will be flowing through these transmission lines, what would happen is like we'll be having higher losses, like losses that will be equal to I square R losses will be very high, because our current is very high and I square high will be much more. And we know that the span of these conductors or like cables is hundreds of kilometers, like therefore our current, like this losses will be very high. That would be a efficient system. So what the idea here is, like we want to go for higher voltage levels in order to decrease the current and so as to reduce the losses. So that was for it. So another that is with regards to high voltage, why we go for high voltage transmission. So now what we want to see is, why would we go for a DC transmission? You can see, you know that like in an AC, uh, like for the AC, like you would have read like we are having like when AC will be transferring with at higher voltages at a certain frequency, will be having certain effects like skin effect and proximity effects are there. And uh, which can like increase the size of our conductors, like that flow, like due to the skin effect, like the current is flowing through this through the outer skin area of the conductor. And with, if we go and some other like asynchronous interconnections, and if we want to like connect at different lines, and let us say one is at some other frequency and other is some other frequency, like it is very difficult to like to synchronize them. With this DC, like what we are able to achieve is like the size of the conductors are like decreased, and we don't come with these effects like skin effect, and we don't see these effects in this DC transmission. And in terms of that, this is like quite economical in terms of this the windings, like over these cables will be able to reduce the overall like size of these cables, and which will be quite economical. But the on the disadvantage, like the disadvantage is like we'll be having to use more number of converters here. Like firstly we'll be in the generation stations we'll be generating these power in AC, and first we have to convert this AC to DC at higher power and voltage levels. So we'll be using large converters, probably the multi-level converters, to like have that AC to DC first, then we'll be having then transferring the DC. And at the receiver side, first we have to step it down, like we have to convert that DC into the AC system. Like we have to use this large converter system, which will be very expensive, and the reliability will be also there. Like will be using the converters, and reliability will be one of the issues here. Like we'll be using more number of the switches and all. So yeah, that will be having some pros and cons, like we have to see now. If our pros are more like what would like be more to us, like we have to optimize them. Like if you are getting like more economical advantage, or then we can switch for the HVDC. Like, and currently a lot of research is going on in this HVDC transmission, how we can like do the transmission in the HVDCs. So coming to this HVDCs, like we have like two systems. Like one is this monopole system and another is the bipolar system. So what is this monopole system? As this name suggests, it is they will be having the one polarity or monopole, like single polarity. What we'll be having here is like an AC three-phase AC system is generated from a generation station. Then we have a transformer. After that, what we'll be having, first we'll be having a converter that will do the rectification from AC to DC. And you can see from this converter only this one line, that a positive line, one line is like we have a one transmission, like from this converter, from AC/DC converter to the other end, where we'll be having another converter that will act as an inverter, that will like do the inversion operation from DC to AC, that will be having going to the subgrids and all. Then we'll be having conversion from AC to some other voltage levels. And this ground will like will be having the line of one polarity, let us say positive polarity, and this ground will provide the return path for that. And in this bipolar system, what we have is similar to the monopole. We'll be having an AC like generation, then a transformer, followed by this it will be a DC AC to DC rectifier system. But compared to this monopole, here we'll be having one DC line that will be of a positive polarity, and another DC line that will be having of the opposite polarity and negative polarity, that will be developed by these converters. And the ground will be will be having a ground wire will be, and another wire will be common to both. So here the what here we have to see is like will be at the source end will be having a converter that will be doing the rectification operation, and at the load or the output side will be having a converter towards the load ends, where we will be delivering to the loads to the consumers, and all will be first having a converter that will be doing the DC to AC operation. So here you can see in like both things, like two converters are needed, like one at the source side that will do the rectification operation and another towards the load end that will be that will do the inversion operation. So you can see like the operation like the option C is correct, like one will act as a converter that will be doing the rectification operation, and other will have to act as an inverter that will be doing an inversion operation. So question number 3, coming to the question number 3, for high power applications dash are used as static switches, whereas the low power applications dash are used. So anyone can answer? Can anyone answer this? So one of your answer is B. So like we'll be seeing this option B is the correct one. Now we can see this like what we had discussed in the first or like second problem solving session. We had seen like we are having different like types of switches that operate at different power level and frequency levels. So here you can see that the x-axis shows the frequency, and here like this is the power level. So here you can see these thyristors, if you can see, these operates like of megawatt level power levels, and after that, but they will be operating at lower frequency, but they will be operating at lower frequencies. And these transistors like this will be having like GTO, you can see that they will be operating some at higher power levels but less than that SCRs of thyristors, but with some more towards the higher frequency range. Then comes our IGBTs. They will be operating at lower power levels than that of SCR and GTOs, but will be operating at higher frequencies. And after that, you can see the MOSFETs, they'll be operating at much more higher frequencies, but the voltage blocking capability of these MOSFETs and the power is very less compared to the SCR IGBTs, and so on. You can see BJTs, they are low power, but they'll be operating at higher frequencies. So you can see that this has been discussed in much more detail in these first lectures. You can go through those lectures and notes, and probably there's problem solving sessions, the recorded problem session that has the links of which have been shared with you. uh, so you can go through this. This has been done in detail, why these are operating at these lower frequencies, their circuitry, and what are their structure and all. So here you saw these thyristors are operated for higher powers but low switching frequencies, and these transistors are operated for uh, lower power applications. So this, for high power application we use SCR, and for low power application we'll be using the transistors. And so this option 3 is the right option for this. Coming to the fourth question. So fourth question, here we are: determine the loss of a snubber circuit. So what is given is a snubber circuit. I think this snubber also hasn't been discussed during this course, so I'll be giving you an idea what this snubber is. And what is given is we have this snubber. If C is 0.545 microfarad and the supply is 221 volts at 10 kilohertz, so what will be the loss of this snubber circuit? So you can see this snubber circuit is used to limit, we have to limit dV by dt or di by dt. Since here RC snubber is given, so here RC snubber is used across switching device to limit the dV by dt in this switching, to limit the transients and all in this. As we know, this voltage cannot change abruptly in this capacitor won't allow the abrupt change in the voltage. So this capacitor is used across this switch to limit that dV by dt change in this dV by, and what this R is whatever the energy that has been stored in this capacitor, we have to dissipate that energy somewhere. So this R is, we had dissipated this energy through this R. And now if you want, there is another snubber that we use, is an inductor. So that we're using to limit the di by dt, and that will be connected in series with the switch, because current flows in the series and voltage comes across. That's why this is connected across the switch. And if we want to limit rate of rise of the current, there we have to use and inductive snubber. This is a capacitive snubber, they will use the inductive snubber in series with the switch. So now we know that this snubber is connected across this switch to limit this voltage rise. And now I want to see what is the power loss. So here we can see the energy that is stored, that will be stored in this capacitor, will be equal to 1 by 2 CV square. So the energy stored in this capacitor is half of CV square, and we know energy will be equal to power into time. So if we do P into T, or T we can write by 1 by F. So it will be equal to power will be equal to energy divided by time, and 1 by T we can write as F. So here the power that will be across like this and dissipated because of the energy that will be stored in this capacitor will be equal to like P. We have 1 by 2, like the value of this C is given, that is 0.545 microfarad, and also this voltage is given to us, that is 221 volts. So this is the amount of energy that will be stored in this what can I say, like in this capacitor. So the amount of power that will be dissipated will be into the frequency that is given is the 10 kilohertz. So the power that will be dissipated across loss because of this number will be equal to, like if we like can do the calculation, it comes to be equal to 133 watts. So the loss of the snapper circuit will be equal to like 133 watts. That is the answer to this question number 4. Coming to the question number 5, here what is given is like, this is the question on HVDC transmission. So we saw in the HVDC transmission we have and two types, like a monopole system or a bipole system, where we have like one voltage and two voltages, and at the source we had a converter that was doing an AC to DC rectification, and then towards the load side we're having a DC to AC that was doing an inversion operation. So here what is said is like two 6 pulse converters used for bipolar HVDC transmission systems. Like we will be having a 6 pulse converters, and the transmission is like bipolar, that means we will be having two poles, and the system is rated for 100 megawatt, and we'll be having the voltage, since it's a bipolar system, that will be having two lines, one of like plus 200 kV and other will be of minus 200 kV. So what we have to see is what is the DC transmission voltage. Can anyone guess this? I think this is quite simple. Anyone with the answer? Like we have the options of 200 kilovolt, 400, 500 or 100. Anyone with the answer? Anyone? No one is able to like answer this question. So let us see. So we saw like we have a bipolar system here. So when we'll be having a bipolar system, so one line will be at a potential of plus 200 kV, like we'll be having an AC by 3, after that we'll be having some transformation and then some rectification will be doing, and that will be generating, this converter will be generating plus 200 kV, and this converter will be this line will be at a potential of minus 200 kV. So here you can see overall DC transmission will be between this line and this line, that will be equal to, like if you can see, this will be equal to like plus 200 minus 200, that will be equal to overall, like we will be having a positive DC line potential with respect to ground at like 200 kV, that what I had told, like with respect to this, and negative will be at like this line will be at minus 200 kV. So if you can see the total potential from this line to this line will be having a 400 kilovolt. So overall, like DC transmission voltage will be like of will be getting a 400 kilovolt we can get here. So the correct option to this is like option B. Option B is the correct option. This question number 5. Question number 6. The converter circuit which employs turn on and turn off when the voltage or current through the device is 0 at the instant of switching is called a conventional converter, a multi-level converter, a matrix converter, a resonant converter. So I don't think like you will be familiar with that. Like this hasn't been touched in this course, but I don't know why they have put up this thing in the course. So what the question is asking is, we will be turning on or off we'll be turning on or turning off our devices only when we'll be having like voltage or current through their devices will be zero. That will be, we'll be doing a zero voltage, like zero voltage turn on and zero current turn off for these devices. So if you can see the conventional converter, like you can see there, like there is some voltage and current that is flowing will be there when we'll be turning on our device. You can take a example of a buck converter or a boost converter. Then there is another option of a multi-level converter. You saw with the multi-level converter that it was able to like reduce the switch voltage stress, but you can see there as well, like there is not an option uh, like uh, like conventional multi-level converter won't be getting, like due to this multi-level we won't be getting a zero current or zero voltage and zero current turn on or turn off. Then there is a matrix converter which we saw in this last lecture, and where we saw like it is a direct uh, AC to AC transformation, and there you can see as well, like there also the switching is not at zero voltage or zero current. Now there is another class of converters which we called resonant converters. This is the correct option to this question, like the resonant converter. You just keep it in mind, like we have like different types of resonant converters. Like each resonant converter cannot achieve like both. We have certain converters that achieve like ZVS, like zero voltage turn on, but still there can be zero current. There won't be zero current turn off. We have some resonant converters which can have both zero, which can have only like zero current turn off, and there are some converters which can have both zero voltage as well as zero current. So how this, like I'll be giving you the brief overview, like this is a detailed topic, how this is happening, how this happens and all, like going into the intricacies of it. Like this is like quite a topic for the whole semester, but the brief idea here is, in the resonance converter we'll be having some L and C that will be forming some LC network, that will be forming some resonating network between this L and C, and in this L and C we'll be having some sinusoidally varying voltage and current. When due to this LC network we are able to have this sinusoidal voltage or current current, and you know, like when we having a sinusoidal voltage or current, we will be getting to a point where this voltage or current can be zero, because like now instead of having some positive value and ripple, with some ripple we'll be having some sort of a current through our devices that will be sinusoidally varying, be it for a portion of a time or for the whole time, and we'll be getting at a point where this current and this voltage will be zero. And if we are able to switch at that moment of time, like we can uh, first, like also what I would want to say, why we want to go for this zero voltage and zero current switching, you know, like when we had seen in these earlier classes, and at the time of switching instant, like we know that this voltage doesn't change instantly from one level to another level, and similar is the case for this current, that it doesn't change from one level to another instantaneously, and there will be some time duration during which like this voltage and currents overlap, and during that amount of time there will be some switching losses. And in order to reduce, like higher the frequency, like we'll be operating our converters, and higher will be our switching losses. So in order to reduce these losses, what we want to do is we want to have either one of these, like voltage or current, zero at the time of the switching. So whenever we switch the device, turn on or turn off, so our losses will be minimized at our switching interval, so we can push for higher frequencies. That is the idea behind using these resonant converters. And for that, like we'll be having these resonant converters will be these resonant converters utilize an LC kind of a network, and these LC converter network, like they resonate, and due to that we'll be having some sinusoidal voltage or current, and like we'll be because of this sinusoidally varying, we'll be getting at a point where we'll be having our voltage or current will be zero, and we'll be switching our device at that. So the advantage, like I told you, like we'll be getting reduced losses, because like at the time of switching, one of these parameters is zero, and if we like turn on the device at that interval, like we will be having a minimal losses. And there are like some disadvantages, like we have to these resonate, we have to like have some more extra components, like an LC. You'll be seeing, you can see this resonant converter. This there is a one chapter on this power electronics converter by Robert Erickson. You can go through that and see in detail. In the third edition, you can see it in detail how this like resonance happens, and how we can achieve like the zero current, zero voltage switching, and all that is given in much detail in there. And like these resonant frequencies, like that will be determined by these components L and C, like we have to choose them. And then our like also, like we have to optimize, use this more number of devices, that is on some things that are on the disadvantages side. But there is some advantage that will be providing, that will be getting a lower, I won't say like this is an advantage, like the disadvantages, they are difficult to optimize using the more number of components, but certainly we'll be getting a prospect in terms of a reduced losses. So but the difficulty comes in terms of like optimizing these components and resonant frequencies and all, like you will be going through the variation, different parameters, how they are designed and all. Like, so here you can see, I have put up an example of this like a Xerxes buck converter. Here you can see, if you remove this L and C, we'll be having a buck converter where we'll be having a switch S, and we'll be having inductor, diode, and this. And you can see then, to have this RCS operation, we have like utilized an additional like this L and C component. And you can see this when this like switch is like on, you can see this L and C will resonate, like this current through this inductor won't rise, like it will first rise linearly up to this load point, and after that like this L and C will start to resonate, and this voltage across, initially there will be some voltage that will be across like this uh, this capacitor, and it will start to fall, and like the current will start to like uh, this voltage, and they will start to like resonate here. current voltage will fall and current will rise in a sinusoidal fashion. Like you'll see it in detail if you go through this book that I have already mentioned. The idea here is like at the time of turn off, you can see like here IL has gone to 0 at this point, and after that it stays 0. So during this portion of time, like we can like whenever this IL goes to 0, after that we can turn off these devices. That means if we turn off this device, that there will be no current that will be flowing through this device at this moment, and will be minimizing the losses. But during the turn on, you can see there is some voltage across this, and but there is no current here. So current was already when we turn on, there will be some voltage, and after this, when this current will rise to its load current value, it will first it will like linearly. After then, these two will resonate from this point. This voltage will start to decrease. That will be across this switch sinusoidally. So here the idea is whenever this current goes to 0, we'll be turning off our switch. That our switch will be turned off at 0 current interval. So there is a I would like understand, you won't be understand how this is happening at all, and that is not quite possible at this moment of time to explain it in detail how this happens. That we have to go write the equations and see how we are coming up towards these equations, how these resonate. And you can certainly like search for this resonant converter topic, and you can see it, read it in much detail. So the correct option is this resonant converter, D option. Now coming to this seventh question. The reverse recovery time of a diode is given, like TRR is 3 microsecond, and the rate of fall of the diode is given also, like that is di by dt is given, that is 30 amperes per microsecond. Determine the storage charge. So we have to see how much charge is stored in during this reverse recovery time. So we know like in these diodes, whenever this is like forward bias and when we reverse bias, there is accumulation of charge in this space, and to this there will be some reverse, to eliminate these there will be some reverse recovery. So it will be like this diode current will first come whenever we like turn off this device, will go to 0, and then we'll be having some negative value, and it will go to the peak of this IRM is the peak of the reverse recovery current, and then it will come back to the 0. During this portion, like this space charge carriers are eliminated from the diode. You can go through the diode that we had earlier discussed in these earlier courses, how like diode structure, what is this reverse recovery and all. So if we know this TRR or TA and TB, and we know this slope of this, we can this is the charge that has been accumulated in during the reverse recovery. So if you can see, the charge that has accumulated will be given by the area of this triangle. So if we know this base and we know this altitude of this triangle, we can calculate like area of the triangle is half a base into altitude. So we know that we have first what we'll be doing, like we'll be calculating this peak point. So this peak point, what will be, it will be equal if we like know this time interval, like this time interval TA time interval, if we know, and we know this rate of change, we can calculate this peak point up to which it can go. So here we can see IRF peak will be di by dt into TA, that this rate of change multiplied by this time duration. Also you can see here like this TPB is like very minimal here in this case. So here in this case this it has been neglected. So when this has been neglected, we assume here like TRR is equal to TA. So here like di by dt is given, TA is given, TA is not given, like we assume TA is equal to TRR. So IRM will be equal to 30 ampere per microsecond into 3 microseconds. That will come out to be equal to 90 amps. So here it will be equal to 90. This. Also like we know like this TRR is equal to TA, we can assume like this is equal, like then we can assume we can calculate the QRR, that will be equal to 1 by 2 into base, we calculate IRM will be equal to 90, TRR is equal to like 3 microseconds. So we'll be getting equal, if we do it will be equal to 135 micro coulombs. So option B is the correct option of this. Option B is the correct option. So another like question, now coming to the question number 8, triac. We have to see triac is used in, like first is a chopper, speed control of induction machine, speed control of universal motors, and none of the above. So can anyone guess like what is the answer to this question? So I don't think so. Speed control of the induction machine, one of you has like so we'll be seeing. So here firstly I'll be discussing this structure of the triac. Here triac will be having two SCRs that will be connected in the anti-parallel fashion, and they'll be having a common gate. Here you can see like since they are like like SCR, we have this both they are able to block the voltages in both directions and are able to conduct the positive current. Since we are having these two SCRs in anti-parallel, that this triac is able to conduct the current both positive as well as the negative current, and it can block both positive as well as the negative voltage. So that was about the triac, like we saw this triac. Now we will want to see where in our application where we'll be using this device, where we'll be needing both like bidirectional voltage blocking capability as well as the bidirectional current carrying capability. So firstly like we'll be going through the motor speed control of this induction machine. So here what is done is like we'll be having some AC supply. We will be doing first AC to DC. We'll be doing the rectification. Then we'll be using an inverter, and this inverter like we can operate, and which is used to operate the induction motor. If you want to do the like V by F control of this induction machine, like we can like change the modulations of this induction, like we can use it change the modulation of this inverter portion of this, and we can vary this speed of this induction motor. And here you can see for this induction motor what we need are switches, like our switches should be able to have this bidirectional current carrying capability, and here we can use the devices like IGBTs and the MOSFETs. So it has to, like whenever there is current positive current is being conducted, it will be carried through this IGBT, and whenever there is a negative current, that will be carried through this diode. So here in the induction motor control, we won't be needing any they don't have to, these switches don't have to block the negative voltage, negative current is being carried by the anti-parallel diode, and we don't be needing the triac for that. And now coming to the universal motor, like universal motor is sort of a motor, if you like check it and go into the detail of it, like it works with both AC and DC. So here like we have to, like for this AC, it has to conduct block both positive and negative voltage and conduct both this positive as well as the negative current. and it has to work with both and ACs. And in case of this universal motor, like we'll be using the triac to control this. So here the option C is the correct option for the speed control of this universal motor. Now coming to the question number 9, which of the following indirect matrix converter allows only unidirectional power flow? So we have certain options like ultra sparse matrix converter, sparse matrix converter, very sparse matrix converter. So here, like we saw in the last week, like matrix converter has two types, like direct and indirect type. And what it does is like it reduces the direct AC to AC transformation. A direct indirect type, like direct does is direct AC to AC transform, but what is done is in the indirect matrix converter, like this first AC is converted to the fictional DC here, and then it is converted to the AC. So there is a between like a DC stage. So now we want to see this which of these allows this unidirectional power flow. So first we will be seeing an indirect matrix converter. The circuitry of this is like this. Here you can see we have like two 4-quadrant switch at the input. So we will be seeing if it is able to like to have the unidirectional option, it should be able to conduct the current in only one fashion. So if you see the current here, whenever this current is positive, then one of the switch and one of the diode will conduct, and when the current is negative, then one of this switch and this diode will conduct. So in case of indirect matrix converter, it is able to conduct both the positive as well as the negative current. Now coming to the sparse matrix converter, how is sparse matrix converter different from this indirect matrix converter? You can see like will be having if you can see this lower devices, we have a one switch less compared to this indirect matrix converter in each leg. And you can see still here in this sparse matrix converter, like it is able to, if you can see here, like this positive current will flow from this switch, and this take it from like C. If you have a positive current here, like it will flow through this diode and this here. You got it? And if you'll be having a negative current, that will flow through this and this point here. Like this sparse matrix converter is also able to conduct both positive current and negative current. Now coming towards the very sparse matrix converter, here we will be having like as one more switch is reduced in the topmost device, but still you can see if you take like a C, like if we can see it is able here the current, if we have a positive current, then the switch and one of the devices will conduct, like positive current will flow through this sort of a way, and we'll be having some negative current that will flow through this. Now will the ultra sparse, like there will be no switches, only the diodes in this like lower portion and the positive current only. So if you can trace this C leg, we can see whenever there is a positive current, it will flow through this diode, then switch and this diode. But however, if we are having a negative current, it has no path to flow that that negative current. If you like can see my cursor, if you there we have a current direction in this direction, and there is no path to flow that direction. So the ultra sparse matrix converter one will only allow the unidirectional power flow. So option A is the correct option. Then comes to be question number 10 and the last question, and the transfer function approach is applicable to A is only linear time invariant system, linear time, B is linear time invariant system as well as linear time varying system, C is linear as well as non-linear system, and D is all the systems. So I don't think the option to this question is like the transfer function model is applicable to the only linear time invariant systems. Like you have to see this is like the control aspect of it. If you see the control aspect, go into the detail, like you can see that we do this transfer function approach to control for the controller design and all, like we do for only the linear time invariant system. Like for this linear time invariant as well as time varying system, we use like the state space and all things. And read in detail, you can like take a course for this control, or see like a book like Control System Engineering by Norman Nice and all. So yeah, that was it for today, and I hope like all these sessions were fruitful and helpful in a way. Like this will certainly help you in solving your assignments. And this is this was the last uh, problem solving session, and we'll conclude here. And if you have any questions, like you can ask, and if you don't have any questions, then we can uh, conclude here. Okay, thank you so much, and thank you for bearing. Okay, so we'll be concluding here, and that is all from my side, and thank you for joining in every session, whosoever have joined. And if some have joined for certain sessions, thanks to them as well. Okay, that was it for today. So okay, we'll be closing our session here. Okay, thank you.